Good days to all and our dear Dr. Muhammad Afiq. Our team's title is Toxic Metal Contamination in Seafood and the Impact on the Consumers. The following are our team members, which are Sandra Oyong-shin, Yap Ju-sing, Cha Wai-san, and Lee Xuan-ying. So, I'm Sandra Oyong-shin and let me introduce the introduction of our topic today. Basically, what is mussel? Mussel is a type of seafood which is an important source of protein and nutrients for human consumption. It contains 60% of proteins in 100 grams. It is found in abundance along the coastal marine waters because of its rapid growth. The mussels are vulnerable to red tide and other harmful algae blooms. Therefore, they could easily accumulate toxins and those who consume them may become very severely ill. The mussels are cultivated as seafood cuisine because of their economically valuable as they multiply quickly and in large number. In this context, Johor has the largest producer of P. viridis mussels in Malaysia. Its major harvesting area is at Kampung Pasir Puteh, which is near to the Pasir Gudang seaport and the industrial zones. Okay, from the graph, we could easily see that the sampling site is located very near to the seaport and the industrial zones. Therefore, the possibility of increasing contamination by toxic metals from the seaport and industrial activities into the surrounding seawater where the mussels are bred could not be ruled out. It is found that the Kampung Pasir Puteh has been exposed to petrochemical and its related industries, as well as shipping, land reclamation, and urbanization. The consequence of the acute exposure to high levels of toxic metal may result in brain damage, paralysis, anemia, and as well as the damage to reproductive, immune, nervous, respiratory, and cardiovascular system. Following that, the chemicals that could potentially found in the mussels. In this context, the concentration of heavy metals contaminants, namely the lead, cadmium, copper, and mercury in P. viridis mussels and their surrounding seawater samples from multiple sampling locations in the vicinity of Strait of Johor are investigated. The source of copper contamination may originate from the industrial effluents, municipal waste outfalls and sediment dredging, as well as from leaching of antifouling paints of ships entering the marine and estuary waters. The ecotoxicological studies performed on P. viridis mussels at Kampung Pasir Puteh between 1998 and 2009 have reported the substantial amount of lead and cadmium, and because similar analysis on such mussels sampled beyond 2009 remains unavailable, this present study that evaluated such aspect acquires considerable pertinence. For your information, according to the Food Act and Regulation 2013, the maximum allowable levels of lead in Malaysia is 1.5, for cadmium is 2.0, for copper is 30.0, and the mercury in mussels is 0.5 microgram per gram. While for the maximum concentration of lead in marine water is 8.5 microgram per gram, for cadmium and copper, both are 2.9, while for mercury is 0.16 microgram per gram.
Good day to Dr. Afiq and my fellow teammates. I'm Cha Wai-san, so I'm going to talk about the sample preparation method. First of all, what is sample preparation? It is a process that extracts and pre-concentrates the compounds of interest from the matrix, eventually making the sample more suitable for further separation and detection. But why we need sample preparation? It is because raw samples cannot be inserted directly into the analytical instruments, as they might carry contaminants and impurities that can bring damage to the instrument. So by carrying out the sample preparation, it helps to improve the accuracy, prevent contaminations, and lastly lower the risk of results distortion. So let's move on to the first method, which is microwave-assisted wet digestion. Wet digestion is a method that involves the usage of strong acid in order to increase the solubility of the sample through chemical degradation of the sample matrices in the solution. Various types of acid can be used for the treatment and usually carried out under high temperature in a specially designed closed system. Microwave digester is an instrument that is widely used in sample preparation. The figure on the right shows how the microwave digester looks like. The microwave vessel in a closed system, which can isolate the sample completely from the surroundings, avoiding the contamination of the samples by the air, environment, and the vessel walls itself, thus allowing the complete digestion to occur. Microwave-assisted wet digestion has its own advantages. First, the use of acids increases the solubility of the sample. Since the microwave digester is a closed system, it can avoid sample contamination. Lastly, the decomposition of the sample requires only a short time and less reagent is consumed. For the disadvantages, there is risk of explosion and cracking of the digestion vessels as the internal pressure will increase as the temperature increases. The cost of buying this instrument is also high, thus it is not affordable for most people. The next sample preparation method is dry etching. It is one of the most commonly used sample preparation methods. It involves the use of a temperature programmable muffle furnace between 500 to 600 degrees Celsius. Under such high temperature, water and other volatile components are usually vaporized, while the organic substances are burned out by consuming the oxygen present in the muffle furnace to carbon dioxide, water, and nitrogen. While for minerals, they will be converted into oxides, sulfates, phosphates, chlorides, or silicates. Both of the minerals are resistant to this high temperature. However, some minerals such as iron, lead, and mercury may be partially lost at such high temperature. For the advantages, dry etching method is commonly used because it is safe to apply. It requires few reagents only, and many samples can be analyzed simultaneously. Furthermore, it is not label intensive and the etch can be used to analyze the wanted specific minerals. However, it requires a long time, usually 12 to 24 hours, hence it leads to high electrical costs. Moreover, it is not suitable for temperature-dependent minerals such as copper, iron, lead, and so on, as they are volatile and may decompose at high temperature. The last sample preparation method is wet digestion using strong acid. It is a popular and simple sample preparation method in chemical laboratories. For this method, acid attack occurs in open containers such as Erlenmeyer flasks and screw-top vials that are placed on a hot plate. It is commonly used due to its high control flexibility on the parameters such as temperature, time, and the addition of reagents. However, since it is digested openly, there is risk of contamination from the laboratory environment and air, as well as loss of volatile elements. Last but not least, large amounts of reagents are required for complete digestion of the sample.
Greetings to Dr. Afiq. My name is Li Xuanyin and I'm going to proceed with the Part 4 Sample Analysis Method. So after reviewing 5 journal articles, as discussed in our report in this case study, we could summarize that there are 4 main analytical techniques available for detecting the heavy metal analytes, all which are related to our topic, which is the toxic metal contamination in seafood and the impact on the consumers. The first type of analytical technique is the atomic absorption spectrometry, AAS. It can be further classified into flame AAS, graphite furnace AAS, cold vapor AAS, and hydride generation AAS. The second available technique is the inductively coupled plasma mass spectrometry, ICP-MS. Third technique is the inductively coupled plasma optical emission spectrometry, ICP-OES. And the last one is the atomic fluorescence spectrometry, AFS. Now let's start with the first type of instrumental analysis, in this case which is the AAS. I will explain more on the similarity and differences between each type of AAS and their respective pros and cons. Generally, AAS is a spectrometry specified in the elemental analysis by acknowledging the fact that atoms in every element are able to absorb radiation or light at a selective wavelength to excite to a higher energy level. Chemists are able to quantify the amount of analyte present in the sample based on the intensity of absorption presented in the spectrum, with absorption at the y-axis versus concentration at the x-axis. So how actually AAS works? When performing AAS, The sample containing the analyte must dissolve completely in a compatible solvent, for example water. Then an aspirator is used to suck the sample mixture into the nebulizer to mix with the oxidant and the fuel. Then fine aerosol is formed and introduced into a heat source. The heat source atomizes the sample analyte, which are then excited to a higher energy level after absorbing light at a selective wavelength from a light source. The light source can be either a hollow cathode lamp or the more advanced electrodeless discharge lamp. The detector detects the light absorbed by the targeted analytes and generates signals to produce a spectrograph. Now that we already understand the working mechanism of AAS in general, let's look closer into different types of AAS, starting from flame AAS. FAS is the simplest form of AAS. From its name, we know that flame acts as the heat source to atomize the sample analytes. FAS are able to detect metal elements including copper, silver, iron, and lead in a wide range of sample matrices such as biological sample, food sample, and water sample. The advantages of using FAS is that it provides fast analysis, it is economical, and is a robust technique, and has low detection limit in ppm range. However, it possesses many limitations such as large amount of sample usage, low sensitivity, limited to only sample in liquid form, and analysis of different elements would require different lamp. This slide shows the schematic diagram of flame AAS. From this diagram, you can see that the sample and light go through the nebulizer and atomize in the flame. Then, they absorb light provided by the hollow cathode lamp with Cl, and corresponding signals are received by the computer to generate spectrum. The second type of AAS is the graphite furnace AAS. The mechanism is similar to that of flame AAS, only that the atomizer is substituted with a graphite tube that is heated electrically rather than using flame. From the schematic diagram on the right hand side, you could observe the sample is inserted into the center of the graphite tube and vaporized to gaseous atoms. The heat in the confined space in the graphite tube allows more complete atomization. Also, the atoms of the analyte are exposed to even and thorough distribution of light beam due to confined space. Graphite furnace AAS are able to detect trace elemental matter. It is designed to counter the limitations faced in FAS. So, graphite furnace AAS only requires small amount of sample volume in microliter and can accept different states of sample, either in solid, solution, or slurry. It can also provide even lower detection limits until the ppb range. It has undeniably higher sensitivity due to longer reaction time with more complete atomization. Nonetheless, it has lower reproducibility than FAS, and the equipment is more costly. The third type of AAS is the cold vapor AAS. This method is employed specifically to detect and quantify mercury concentration in samples. This is because flame AAS will give low sensitivity result, while graphite furnace AAS will vaporize the mercury. Hence, it is not recommended as well. The cold vapor AAS has slightly different working mechanism compared to flame AAS and graphite furnace AAS. By referring to the schematic diagram, the sample solution and the tin 2 chloride solution is inserted into a gas liquid separator through a peristaltic pump. Then the argon gas, which is inert, is bubbled into the mixture inside the separator to separate out the mercury vapor. The released mercury vapor is then transported to a dryer to remove the moisture, and subsequently to a cell to receive the radiation from mercury lamp. The mercury gaseous atoms absorb light at characteristic wavelength, and the intensity of signal generated is proportional with the mercury concentration in the sample. The equation shown in the orange box is the reduction of mercury ions to elemental mercury by silver ions. Simple operation procedure, very low limit of detection in PPT range, and rapid analysis are some of the advantages of performing cold vapor AAS. However, the major setbacks of this technique are its application is only limited to one type of analyte, which is the mercury, and it usually requires labor force for numerous sample analysis. Next, the fourth method under AAS is the hydride generation AAS. The term hydride in this technique indicates that this method is selective towards metalloid elements that form hydrides, such as germanium, tin, lead, antimony, and selenium, which are mainly elements from the group 14, 15, and 16 in the periodic table. The metalloid elements are first reduced to lower oxidation states using the sodium tetrahydroborate 3 as reducing agent. Then the reduced metalloid forms a volatile hydride that is then carried away from a sample by inert argon gas to the quartz tube to be heated and interact with the radiation that pass through. Hydride generation AAS is able to remove matrix interferences in highly soluble solids that are quite impossible to be achieved by graphite furnace AAS. However, this method is only valid for acidic sample solution, and only narrow range of elements can be analyzed using this method. On top of that, the sample preparation steps would be rather complex because each hydride element required different sample preparation method. Now we have come to the last method under AAS, which is the flow injection mercury hydride system, FIMHS. From its name, we could figure out that this method is actually the combination of hydride generation and cool vapor AAS, with the flow injection as sample introduction technique. Thus, it can be applied in the detection of trace mercury and hydride forming elements. There are definitely many advantages of using this method, including obtaining high yield through automation of hydride generation and amalgamation of mercury, minimize memory effects, receive minimum matrix interferences, less consumption of carrier gas and reagent, thus is cost effective, consists of auto sampler that reduce labor force and increase work efficiency, and most importantly is it has low detection limit. Of course, the price of this instrument with the integration of different features in one machine would be higher compared to other AAS technique. We have come to the second type of the sample analysis technique, which is the inductively coupled plasma mass spectrometry, ICP-MS. The inductively coupled plasma indicates that plasma torch is used to atomize the sample analyte under high temperature of about 6,000 Kelvin to 10,000 Kelvin. The plasma torch will remove solvents, vaporize excites, and ionize the atoms. Then the ionized atoms are conveyed to the mass analyzer in the mass spectrometer to analyze the components in the sample based on the mass to charge ratio. There are several types of mass analyzer, for instance, time of flight, quadrupole, triple quadrupole, ion trap, and Fourier transform. The signal received are detected by a detector and are sent to a computer to generate the spectrum. The advantages of ICP-MS are it possesses very low detection limits in PPT range, able to detect multi-element samples, feasible to most metals and non-metals detection, fast analysis time, and minimal matrix interferences. However, the drawback of using ICP-MS is it provides very limited total dissolved solid tolerance because the larger size suspended solid may damage the instrument. This is the schematic diagram of the ICP-MS. As shown in the diagram, when the targeted ions leaving the plasma torch and pass through the interface to the quadrupole, which is one of the types of mass analyzer, and finally reaching the detector, the whole transverse path is conducted in a high vacuum condition with the aid of vacuum pumps. This is because we want to reduce the chance of ions colliding with other gas molecules in the mass analyzer, as it will interfere with the mass spectrum. The third type of analytical technique available for analysis of heavy metal is the inductively coupled plasma optical emission spectrometry, ICP-OES. ICP-OES applies the same mode of sample analyte atomization as ICP-MS, but the only difference is that ICP-MS uses a max spectrometer while ICP-OES uses a spectrometer, which involves specific light emission with characteristic wavelength. After the analyte atoms are ionized, they jump to the excited state, and when the excited atoms return to lower energy ground state, the energy is released in the form of light emission with specific wavelength. Thus, the amount of analyte present can be determined by the intensity of light emitted. The advantages of ICP-OES application are it is able to perform multi-element analysis, rapid analysis, ability to analyze most metals and some non-metals, low detection limit from mid-ppb to mid-ppm range. Nonetheless, these techniques still possess limitations such as lower sensitivity compared to ICP-MS and have certain levels of matrix interferences. In this schematic diagram of ICP-OES, we could notice that a charge-coupled device CCD is used as the detector in this case. Last but not least, atomic fluorescence spectrometry AFS was used in one of the studies to measure the concentration of metal analytes in the seafood sample. AFS is similar to the AAS to a certain extent, except AFS measures the radiation emitted, while AAS is based on the measurement of radiation absorbed by the analyte atoms. Both AAS and AFS focus on the atomic analysis. The working mechanism of AFS is where the analyte gaseous atoms are brought to excited state after absorbing the radiation provided by the light source at specific wavelength. Subsequently, the excited atoms would not retain at the excited state too long, and when it goes down to lower energy ground state, its energy dissipates as photons, which is in the form of fluorescence. Then, only specific wavelengths are allowed to pass through the monochromator and reach the photomultiplier tube detector. The photons then are converted to electric current and generate signals to be read by the computer. The pros of AFS application are high sensitivity and selectivity, low background noise, hence low spectral interferences, and good linearity. While on the other hand, the cons of AFS in analysis are it is susceptible to self-absorption at high concentration, hence will affect the analysis accuracy. Moreover, the short lifetime of the fluorescence may affect the sensitivity of detection, and we must always keep in mind that not all atoms fluoresce. Hence, this method can only be applied to certain atoms that have fluorescence property. Lastly, the diagram below shows the mechanism of AFS. There are two monochromators in AFS, which are the excitation monochromator and emission monochromator. The excitation monochromator selects the desired wavelength of the excitation light, which is focused at the sample position. The emission light, which is of longer wavelength than the excitation, is filtered by the emission monochromator. This selects the wavelength of the light that reaches the detector, which is typically a photon counting photomultiplier tube, PMT. Double monochromators provide better stray light rejection and therefore a higher signal-to-noise ratio for the instrument. The excitation and emission paths are set at an angle of 90 degrees to each other to minimize the fraction of excitation light entering the emission arm.
The sample preparation method that we are going to propose to determine the toxic metal contamination in seafood is by microwave-assisted wet ligation. This method is chosen due to the shorter decomposition time of the samples and less reagent is consumed. At the beginning of the experiment, collect the muscle tissue from different species. Next, clean the samples by using clean water and homogenize it. The samples are stored in freezer at 20 degrees Celsius. A stainless steel knife is used to remove the bone of the muscle tissue. Next, 5 ml of 65% nitric acid was mixed with 5 ml of ultra-pure water to prepare the digestion solution. Samples are placed into the digestion vessel, followed by the addition of digestion solution. Microwave digester was set to 600 watt, 10 minutes flame time, 450 psi pressure at 180 degrees Celsius in 10 minutes. The digester samples were placed in the vacuum tube and added with some ultra-pure water. The instruments that we use to analyze the contamination of toxic metal in seafood are ICP-MS and ICP-OES. ICP-MS was used for lead, cadmium, and arsenic analysis, while ICP-OES was used for aluminium analysis because it usually presents in trace amount. Table 2 and 3 show the ICP-MS and ICP-OES operating conditions and measurement parameters respectively. One shows the ICP-OES instrument. It provides no detection limits, multiple elements, limited spectral interference, good stability, and low matrix effects. Figure 2 shows the ICP-MS instrument. It has low detection limits, multiple elements, and isotope analysis. In conclusion, the presence of heavy metals in seafood will have negative impacts on consumers' health. Thus, it is important to determine the heavy metals contained in seafood. There are different kinds of heavy metals which include lead, cadmium, arsenic, and aluminium. According to our study, the best sample preparation method is by microwave-assisted wet digestion. It increases the solubility of the sample through chemical degradation of sample matrices in solution. On the other hand, the most efficient sample analysis method is by using ICP-MS and ICP-OES. These instruments are selected due to its low detection limits and multiple element analysis. It helps to minimize the negative effects on human health by determining the heavy metals contained in the seafood.